So last time we introduced Laplacian expansion, that definition for computing the determinant. And the way we learned to do it, we learned to expand across the first row when you had like a 3 by 3 matrix, or even a larger matrix. You could do that as well. So it turns out that there's a nice theorem that says it doesn't matter which row or which column you expand across. You can expand across any row or any column, and you'll get the same answer regardless of the row or column. This is going to be called, I'll call it Laplacian expansion. Works for any row or column. That'll be my summary of it. I'm just going to say that. Laplacian expansion works for any row or column. All right, so let's do an example where this would be useful. Here we go. Pen. So let's compute the determinant of another 3 by 3 matrix. Well, let's say my matrix here is 1, 0, 5 down the first column. Down the second column, 5, negative 2, 0. And down the third column, 7, 4, 8. Now, what I'm going to do, I'm going to set up my signs first. My signs. So here I'm going to start off with the 1, 1 entry. First row, first column is going to have plus. Then I alternate signs, minus, plus. Then down the second row, so notice in the second row you start with a 0. That's underneath a plus, so I'm going to put a minus. And then the next entry, negative 2, I'm going to put a plus. And then the next entry, I'm going to put a minus. So these should all alternate. Now, in the third row, I got a 5, right? I have a 5. That's below a 0 with a minus, so I'm going to put a plus on that one. Then the one that follows, the 0 that follows, is going to have a minus. And then the 8 there is going to have a plus. So no plus should be immediately left, right, above, or below another plus. Pluses and minuses should be directly next to each other as far as left to right and above and below. Now, diagonal doesn't matter if you have pluses besides each other or minuses besides each other diagonally, but side to side and above and below, pluses and minuses should alternate. Now, the question is, which row or column would you want to expand across? Well, it turns out it's really nice if you expand across either the second row, because there's a 0 in it, it's going to make your calculations easy. Or you could go across the third row, right? The third row, because there's a 0 in it. Or you could expand across the first column, because the first column has a 0 in it. I'm going to decide to expand across the first column, because we haven't done a column yet. So the way you do this, you're going to start with, so I'm going to write determinant of 1, 0, 5, 5 minus 2, 0, 7, 4, 8. And we're expanding across this first column here. And our signs, I'll do in black here. Plus, minus, plus. That's what's important here. All right, so let's begin expanding. Our own color. Okay, so I'm going to start off with this first entry of 1. It has a plus in front of it, so it stays positive. We're going to do the determinant of the submatrix. So imagine you cross out the first column, the first row, and you have a submatrix of what? -2, 4, and then 0 and 8. Okay, so now I'm going to go on to the next entry in that first column. We're going to have a minus in front of 0. Right, we alternated signs. The sign there was a minus. We're going to have minus 0 times the determinant of the submatrix. Now, do I actually need to write down the submatrix when I cross out the first column in the second row? No, because 0 times anything is going to be 0. We don't even have to bother thinking about what that submatrix is. It's not going to play any factor because we know that's just going to 0 out altogether, because 0 times whatever that determinant would be is still going to be 0. So I'm happy about that, right? I'm happy. It's less work. So anytime you can expand across a row or a column that has a 0 in it, it's a good thing. It makes you end up doing much less work. So now we're going on to the last entry in that first column, 5, and this is going to have a plus in front of it, right? The black plus sign is what we're using there. And we're going to have now the determinant of the submatrix when you cross out the first column in the third row. So the submatrix is 5, 7, -2, 4. Okay, so we got, we basically have reduced this down to two 2x2 determinants, right? Two 2x2 determinants now that need to be calculated. So here I go. I'm going to go down here. So I got 1 multiplied by, okay, so we're going to find the determinant of -2, 4, 0, 8. So let's multiply here down the descending diagonal. We're going to get -16, and then we're going to subtract, and then we're going to multiply up the ascending diagonal. We're going to get 0 times 4 is 0. All right. Now, you don't have to worry about that middle term. We already crossed that out. That's 0. So now we have one more thing to do left. We're going to write down our 5 plus 5 and calculate the determinant of this submatrix, 5, 7, -2, 4. So we're going to multiply down the descending diagonal. 5 times 4 is 20. Minus, then we multiply up the ascending diagonal. -2 times 7 is -14. And we just simplify this, right? This is 1 times -16. And here we're going to have 5 times, let's see, this 20 plus 14, right? That's a double negative. It's going to be this plus 14. That's going to be 34. 5 times 34 is what we have. First of all, we have 1 times -16, -16. 5 times 34 is 170. 170 and -16 combined is going to give you 154. Yeah, so we have a determinant of 154. So actually, an important thing that you should have had at some point in Calculus 3, you should have talked about determinants in there. And it turns out that what happens, what is a determinant? So you would have done this in Calculus 3. Well, if I were to have 3 vectors in R3, 3 vectors, so this is like, I don't know, vector A, vector B, vector C, so 3 vectors. Remember, you can generate what's called a parallelepiped. This would have been something you did in Calc 3, a parallelepiped. So it's a 3-dimensional figure. Right? It's kind of like a cube, except it's parallelograms make up all the sides. And we call it a parallelepiped, something you would have done in Calculus 3. And it's generated from these three vectors. So you have a vector in R3, a vector in R3, and a vector in R3, right? And what the determinant is, so if your first column is A, your second column is B, and your third column is C. So this is going to be a 3 by 3 matrix. You have 3 columns, A, B, and C, and each of these vectors has 3 entries going down. What this gives you is basically the signed volume. So it sometimes is going to be a positive, sometimes it's going to be a negative. Sometimes your determinant will be positive, sometimes it'll be negative, sometimes it'll be 0 actually. It's a signed volume. And the sign, whether it's a positive or a negative, is determined on the orientation of the vectors. So if you actually want the actual volume, the volume of the parallelepiped, you take what's called the absolute value of the determinant. The absolute value of the determinant of that matrix. Yeah. So just a matter of notation. You'll see that in your book. In the book, rather than saying determinant of 1, 2, 3, 4, 5, 6, 7, 8, 9, your book doesn't use that notation. Right? This is the notation that mathematicians use. They actually use det for determinant. A lot of books and engineers, they use this notation for the determinant. It looks like big absolute value symbols. So you'll notice your book actually uses this absolute value looking notation. I don't use that. Not a good idea to use. Not good to use the absolute value notation. Not good to use. And the reason is it gets confused sometimes with the absolute value. It gets confused with the absolute value. So I'm going to be using the det notation, determinant notation. Yeah, so notice when we actually have the volume of a parallelepiped formula here, we have the absolute value, right, of a determinant. So this right here this is actually the absolute value right here. And this is not the determinant symbol, these bars. This represents the absolute value. So the absolute value of a determinant is actually the volume of a parallelepiped. That's something you would have done in Calculus 3 when you studied scalar triple products, something called scalar triple products. When you're talking about a 2 by 2 matrix, let's say you have determinant of vector A, which has only 2 entries, and vector B, which has only 2 entries. So imagine A has 2 entries going down, B has 2 entries going down. You got 2 columns, A and B, so it's going to be a 2 by 2 matrix. This is going to actually give you the signed volume of a parallelogram, signed volume of parallelogram, which everyone should know what a parallelogram is. Parallelogram. So imagine you have a vector A and R2, and a vector B and R2. From that you can create a parallelogram, right? And essentially what that does, it gives you the signed volume, or you can call it the signed area. So typically we call this what? Area, right? Area in layman's terms. Sometimes they actually call it volume. Sometimes they call area volume. It's kind of funny. Yeah. So that would be a plus sign or a minus sign. A plus sign or a minus sign there. So sometimes you get a plus, sometimes you get a minus. It actually depends on the orientation of your vector. So if you have to go from A to B, I believe, counterclockwise, you're going to have a positive sign. If you were to have something like this, let's say A were here, let's say B were here, and you create your parallelogram this way. Notice if when you're going from A to B, you're having to go clockwise. I believe in this case, you would get a negative determinant. Here would you'd have a positive determinant because you're going counterclockwise. Just some interesting facts. Yeah, so if you wanted the actual I should say area. If you want the actual area, if you want the area of a parallelogram, you just take the determinant of the two generating vectors, A and B, and you take the absolute value, right? The absolute value kills off any sign. Yeah, so this is the formula for the area of a parallelogram. You just take the determinant of the two generating vectors and take the absolute value afterwards. So pretty good stuff, pretty good stuff. Yeah, I think I'll stop there right now, and then maybe next we can look at some 4x4 matrices.